Usually when we think about, making a map, there's this ingrained expectation of just straightforward illustration.
Right, like it should just be visual.
Yeah, exactly. You look out your window, you see a winding road and a lake, and you just you draw a line for the road and a blue shape for the lake. You point and say, "There it is. That's our reality."
It feels like it should be highly intuitive. Almost obvious, really.
But step into the world of geographic information systems, and suddenly that simple drawing process is just completely deconstructed.
Completely.
We stop looking at a picture and start looking at this massive, complex mathematical abstraction. And today, our mission is to decode that abstraction.
Because we are tackling Section 201 of the GISP exam.
Yes, the GIC professional exam. We are specifically looking at spatial data models and their associated planar geometries.
Which, I mean, let's be honest, sounds incredibly intimidating right out of the gate.
It really does. And to conquer it, we are synthesizing two very different sources for this deep dive. First, we have this comprehensive, very formal textbook excerpt that covers all the geospatial data fundamentals. It is dense, it's academic, and very thorough.
Very thorough. But our second source is a highly practical transcript from a YouTube creator.
Yeah, and their entire goal is to help you pass the GISP exam without spending, 3 years trapped in those exact textbooks.
Because while this material forms the foundation of how we digitally reconstruct the world, it notoriously gets just bogged down in academic theory.
So our objective today is to translate that conceptual architecture into plain English.
Exactly. We want to arm you with the frameworks you actually need to ace this section of the exam.
So before we can even ask a computer to analyze our world, we have to understand the foundational building blocks, like how GIS actually stores geographic reality.
Right. The storage is everything.
We are looking at the two great pillars of spatial data here, vector versus raster.
The big two.
Most of you preparing for the exam are probably familiar with the vector model. It's coordinate-based. We represent discrete features.
Things with hard, defined boundaries.
Exactly, using points, lines, and polygons, like a connect-the-dots drawing.
And the underlying math there is relatively straightforward.
Right.
I mean, a point is just a single coordinate pair.
Right.
A line is an ordered list of vertices connecting nodes.
Right.
And a polygon simply continues that line until the start node and the end node are the exact same coordinate.
Which encloses the space. And the power of vector is that each discrete feature has its own dedicated row in an attribute table.
The database actually knows what it's looking at.
Yeah, it knows that this specific polygon is, say, a property parcel owned by the city.
But the raster data model approaches the world entirely differently.
Very differently, yeah. If vector is that discrete connect-the-dots drawing, raster is basically a continuous surface.
Like a digital photograph.
Right. We lay a massive mathematical grid over the entire landscape, and every single rectangular cell in that grid gets a value.
We use this for phenomena that don't have hard borders. Because, elevation doesn't just stop at a property line.
No, it doesn't.
Soil pH, ambient temperature, rainfall. These are all continuous phenomena perfectly suited for a raster grid.
Now, the sources bring up a very specific nuance here that feels like premium exam bait.
Oh, absolutely.
Listen closely to this distinction because it's tricky. A pixel is always a cell, but a cell is not always a pixel.
Yeah, they really hammer that point.
It seems like the textbook is drawing this hard line between the mathematical concept of a raster cell like the container holding the data value,
Right.
and a pixel, which specifically refers to the smallest resolvable piece of a scanned visual image.
That distinction really tests your precision of language on the exam, because the cell is a data structure. A pixel is just an illuminated square on your monitor or a dot on a scanned photograph.
Got it. Now, speaking of complex data structures, the sources dive into multidimensional rasters.
Oh, yeah. These are heavily used in earth sciences.
Like oceanography and meteorology, right?
Right.
To capture data at multiple times, depths, or heights. But I have to push back on the visualization here.
Okay, lay it on me.
Wait, if a raster is inherently just a flat 2D grid of cells on an X and Y axis, how does it become multidimensional? Are we talking about, like, 3D Minecraft blocks?
No, not quite.
Or voxels floating in space or something?
No, they aren't physical shapes floating in space. The dimension we are adding is usually a variable like time.
Okay, time as a dimension.
Exactly. So imagine a standard flat raster grid covering the Atlantic Ocean, recording sea surface temperature for today.
Right.
Now, stack tomorrow's temperature grid directly on top of it. Then the next day's grid. You've just created a third dimension, which is time.
Oh, wow.
A multidimensional raster stores all these layered grids as a single cohesive data set. So you can drill a mathematical core through that stack to see how one specific cell's temperature changes over a year.
Oh, that makes total sense. And I guess you can also stack them going downwards to measure ocean temperature at like 10 meters deep, 20 meters deep.
Exactly. That gives you depth as a dimension.
Yeah.
And the textbook highlights several specific file formats engineered to handle these massive stacks.
Which are highly testable, I'm assuming.
Very testable. You have NetCDF, which is the gold standard in oceanography and climate data.
Okay, NetCDF.
Then there is DRIB, used universally for weather prediction models. HDF, which NASA favors because it can handle incredibly complex hierarchical structures of satellite imagery.
Right. NASA uses HDF.
And finally, Esri's Cloud Raster Format, or CRF, which is optimized for cloud computing.
So for the exam, if we see NetCDF, DRIB, or HDF, we should immediately associate them with massive Earth science data and multidimensional rasters.
Yes, and you should also associate them with a fundamental rule of analysis that the textbook really stresses.
Which is?
Matching data scale and resolution. The math of GIS completely falls apart if you try to analyze a highly detailed vector map of local city streets against a low-resolution HDF raster grid of national weather.
Where one cell covers, like, 10 square miles.
Exactly. The computer will run the operation, but the output will just be meaningless. Garbage in, garbage out.
Right, makes sense. Okay, so we have our basic storage structures. Let's look at how we take those structures and actually model the physical ground we stand on.
We're talking surface modeling.
Right. And the baseline here is the DEM, the digital elevation model.
Yeah, the DEM is essentially a bare earth representation. No trees, no buildings.
It's just the literal terrain.
Just the dirt.
Our sources note the USGS, the United States Geological Survey, historically derived these from their 1 to 24,000 scale topographic maps.
Right, the old topo maps.
But today, they are almost entirely generated from LiDAR point clouds. That's where lasers shot from aircraft measure the exact elevation of millions of points on the ground.
It's amazing technology.
Yeah.
And the result is effectively a giant raster grid where every single cell contains a specific elevation value.
And by covering a surface entirely with these grid cells, a raster DEM forms a perfect tessellation.
Tessellation is a great exam word to know.
Yeah, the formal definition is covering a surface with geometric tiles, so there are absolutely no gaps and no overlaps. And squares are obviously the most straightforward way to do this.
But squares aren't the only geometry available.
Which introduces this fascinating vector-based surface model, the TIN, or triangulated irregular network.
The TIN is brilliant.
A TIN covers a surface entirely in contiguous, non-overlapping triangles, but they aren't uniform triangles. The exam focuses heavily on how these are generated, using a rule called Delaunay triangulation.
Yeah, the Delaunay rule is just a stroke of mathematical elegance.
Let me see if I have the mechanics of this right, because it took me a minute.
Go for it.
So if I have a random scattering of elevation points, and the computer connects 3 of them to form a triangle,
Right.
the Delaunay rule states that if I draw a perfect circle that touches all 3 corners of that triangle, like a circumcircle,
Yes, a circumcircle.
there cannot be any other data points falling inside that circle.
You've got it perfectly.
But is the goal just to prevent the computer from drawing, like, really long, useless, slivery triangles all the way across the map?
That is the exact mechanism.
Yeah.
By forcing the circumcircle to be empty, the algorithm basically guarantees the triangles are as compact and well-proportioned as mathematically possible, given the points available.
Okay, but here's the practical question.
Sure.
The sources emphasize that generating a tin from millions of points is incredibly computer-intensive, far more than just laying down a raster DEM.
Oh, heavily intensive.
So if they are so processor-heavy to build, why do we even use tins? Why not just use a standard DEM?
It comes down to adaptive efficiency over variable terrain.
Okay, adaptive efficiency, what does that mean?
Well, picture a raster DEM covering a massive, perfectly flat plane in Kansas.
Okay, flatland.
The raster format forces the computer to store a data value for every single square foot of that plane, endlessly repeating the exact same elevation number.
Oh, I see. It is highly redundant. It's basically wasting hard drive space to tell me the ground is still flat.
Exactly. But a TIN is irregular. Over that same flat plane, the TIN algorithm might just draw one gigantic triangle.
Because it only drops a point where the elevation actually shifts.
You nailed it. However, if the train suddenly hits the Rocky Mountains, the TIN instantly adapts.
Oh, wow.
It generates thousands of tiny, dense triangles to accurately capture the jagged complexity of a cliff face. So a TIN spends its processing power only where the terrain gets interesting.
It optimizes for complexity. That is honestly brilliant.
It really is.
Okay, so we've built our digital terrain using vectors, rasters, dems, and TINs. The landscape is set. Now we need to make it do something. We need to run spatial analysis.
Right. And the YouTube source breaks these analytical operations down into the big three spatial models.
Let's start with the first one, cartographic models. The source notes these basically automate map analysis. They typically use flowcharts like Model Builder in ArcGIS Pro, primarily for multi-criteria decision-making analysis.
Which is really just a fancy way of saying suitability analysis.
Right, layering different variables to find the optimal location for something, like finding the best site for a new hospital by weighing elevation, zoning laws, and distance to major highways.
Exactly.
But the source defines cartographic models as being temporally static, and I kind of struggle with this framing.
How so?
If I am modeling where to build a new hospital, isn't decision-making inherently about planning for the future? How is that static?
Well, you are planning for a future action, absolutely.
Yeah.
But the spatial model itself is static because it operates like a photograph.
A photograph.
Yeah, it takes fixed data layers at a specific frozen snapshot in time. The zoning, today. The rows as they exist right now, it mathematically overlays them to highlight a location.
Okay, I think I see.
It does not generate new time-based data or simulate how things change dynamically.
Right, it's just performing algebra on what already exists.
Yeah.
If I wanted to simulate, say, how ambulances would actually navigate traffic to reach that hospital during a snowstorm, I'd need a completely different tool.
You would. You'd need to move to the third category. Let's touch on the second category first.
Oh, right. Simple spatial models.
Yeah. Simple spatial models take a mathematical equation and apply it across space to predict continuous variables.
So like hydrologic models calculating water runoff volume across a watershed, or statistical equations predicting soil erosion rates based on slope.
Exactly. Which brings us nicely to the third category, your ambulance scenario.
Right. Spatio-temporal models.
These are dynamic in both space and time. Time acts as a literal dimension driving the process forward, and objects actually move and interact across the environment.
And the exam often asks you to distinguish between types of spatio-temporal models. Right?
Yeah, the major divide they test on is deterministic versus stochastic.
Okay, let's break that down. A deterministic model operates like a rigid machine. If you give it the exact same starting inputs, it will produce the exact same result every single time.
Yes, but the real world is messy.
Very messy.
Which is where stochastic models come in. They actually include random generation.
They calculate probabilities, right? Every time you run a stochastic model, it produces a slightly different probable output.
Exactly. The sources point to Landis.
Oh, right, Landis.
It's a famous model administered by the U.S. Forest Service to simulate forest succession and disturbance. And it incorporates stochastic elements because, well, a lightning strike starting a forest fire isn't deterministic.
Right, it's a random probability that alters the entire simulation.
Exactly.
The sources also list cellular automata as a spatio-temporal type. This is fascinating. It's basically a grid of cells where the state of each cell evolves step by step based entirely on the condition of the cells immediately touching it.
Conway's Game of Life is the most famous example of this.
Right, I've played around with that.
You set a simple mathematical rule, like if a forested cell is touching a burning cell, it catches fire in the next time step. The global pattern emerges entirely from those local interactions.
And finally, agent-based models. This is where individual digital agents, like cars in a traffic simulation or shoppers walking around a mall, move across the landscape independently reacting to their environment based on a set of programmed behavioral rules.
So to recap, we have static cartographic suitability, continuous simple equations, and dynamic spatio-temporal simulations.
Which all makes intuitive sense to me, but the GISP exam doesn't just test intuition, sadly.
No, it definitely doesn't.
It tests academic theory. Specifically, the definitions and frameworks proposed by three foundational GIS authors, Bolstad, Goodchild, and Diemers.
This is the part that trips everyone up.
Yeah, the YouTube creator we sourced was visibly frustrated with this section. They pointed out that these academic definitions can feel really disconnected from daily practice. They basically advised just memorizing the keywords and moving on.
I mean, rote memorization will get you through the multiple choice questions, sure. But we can do better than that. If we want these to actually stick, we have to understand the mindset of the authors.
Like why they categorize the world the way they do.
Exactly.
Okay, well, let's start with Bolstad. His framework includes cartographic models and spatio-temporal models, but he distinctly adds network models to his primary list.
Right. So to understand Bolstad, think like a civil engineer or a logistics expert.
Okay.
His addition of network models, which focus entirely on the flow and accumulation of resources limited to connected paths, is all about infrastructure.
Oh, I see.
So if the exam question mentions pipes, roads, rivers, or specifically uses the phrase flow and accumulation, you are in Bolstad's mindset.
Okay, Bolstad is the flow and accumulation guy. Got it. Now, Goodchild approaches it from a completely different angle. He categorizes things into data models defined by entities and fields, and then he splits the operations into static modeling and dynamic iterative modeling.
Goodchild thinks like a physicist or a computer scientist.
Really? How so?
He is deeply concerned with the fundamental nature of the data structure itself. Like, is the world made of discrete entities or continuous fields?
Oh.
So when the exam talks about transforming inputs to outputs versus running iterative predictions at time intervals, you should look for Goodchild.
Okay, Goodchild is entities and fields. And finally, Demers. He categorizes models through these paired opposites: descriptive versus prescriptive, stochastic versus deterministic, inductive versus deductive.
Demers thinks like an urban planner or a policymaker.
That makes sense.
He categorizes models by their purpose and logic. A descriptive model passively observes, like, here's how traffic flows.
Right.
A prescriptive model imposes a solution. Here is the best way traffic should flow.
And then inductive logic builds a general theory from specific data points, while deductive logic applies a general rule to specific cases.
Exactly.
You know, understanding those mindsets actually makes the sample test question provided in the textbook almost laughably easy.
Let's hear it.
The question asks which framework includes cartographic, spatio-temporal, and network models.
Well, because we know Bolstad is the engineer obsessed with networks and flow, the answer is immediately obvious.
It's Bolstad. You know, you really can shortcut the messy theory just by understanding the perspective.
It saves a lot of headaches.
But I mean, none of these complex spatio-temporal simulations or academic theories matter if the computer loses track of where the data actually lives. We really have to look at the basement of GIS, the database.
Data management. It is the unglamorous, expensive reality of the entire profession.
It really is. Our sources differentiate between relational, object-oriented, and object-relational databases. And I like to visualize a standard relational database as this massive, slightly dumb filing cabinet.
Dumb filing cabinet, I like that.
Yeah, it's highly organized into tables, rows, and columns, usually managed with SQL, but the files don't actually know anything about each other.
Right. It stores a polygon's coordinates, and it stores an owner's name, but the database itself doesn't possess any, spatial intelligence about how those things interact in the real world.
Exactly. But an object-oriented database, on the other hand, is like a smart filing cabinet where the folders can actually talk to each other and enforce their own rules.
Data is stored as classes and objects that inherit behaviors.
Yes. A parcel polygon isn't just a random shape. The database understands it is legally bound to a building footprint through what are called relationship classes.
And most modern GIS architecture, like PostgreSQL or Esri's geodatabase, uses an object relational structure.
It blends the two together.
Exactly. It gives you the massive storage capacity and querying power of SQL tables, combined with the intelligence of object-oriented spatial behaviors.
And the most critical behavior in that smart ecosystem is something the sources call topology.
Topology is huge.
But in plain English, what does topology actually do in this ecosystem? Is it just the rule book that stops two adjacent property parcels from accidentally overlapping in the system?
It is the absolute enforcer of spatial integrity. It is a mathematical rule book dictating exactly how features connect.
Okay.
If you draw a river network, topology is the rule preventing an impossible 10-foot gap between two river lines.
Oh, that makes sense.
If you are a utility company, topology ensures your digital gas line is actually snapped directly to the main valve, so a backhoe doesn't dig in the wrong place based on a sloppy drawing.
Because without topological rules, data degrades incredibly fast.
Oh, instantly.
The textbook points out that collecting and cleaning data takes up the vast majority of a project's budget. You have to run constant QA/QC checks, quality assurance, and quality control.
And you must document the origin of every single file using metadata.
Yes, the sources list standards for this, like FGDC and ISO 19115.
Which are definitely on the exam.
Yeah.
If a data set lacks metadata detailing Who created it, when, and to what level of accuracy, a professional GIS analyst simply cannot trust it. It's a liability.
It really is. So for you listening, gearing up for Section 201, let's recap the conceptual journey we've been on.
It's been a lot of ground covered.
It has. You have moved from the coordinate-based boundaries of vector data to the continuous mathematical grids of raster cells. You've adapted to complex terrain using the elegant circumcircles of Delaunay triangles in a TIN.
You have scaled from static suitability overlays to dynamic stochastic simulations running on cellular automata.
You've decoded the academic mindsets. Knowing Bolstad focuses on networks, Goodchild on fields, and Demers on policy-driven opposites.
And you know that all of this relies completely on the spatial integrity enforced by database topology.
You have officially bypassed the textbook fatigue and you are armed with the frameworks you need.
The foundational concepts are locked in. You are ready.
But before we finish, there is a final thought to consider, something the sources hint at but don't quite resolve.
Okay, let's hear it.
So we discussed multidimensional rasters tracking data through time and spatio-temporal models attempting to predict the future.
Right.
As our data collection mechanisms approach absolute real-time with uninterrupted satellite feeds, live traffic sensors, constant climate monitoring, will the boundary between a static cartographic snapshot and a dynamic spatio-temporal model eventually just vanish entirely?
That's a profound question.
If the map updates every millisecond, will our digital architecture evolve from just modeling the world to actually becoming a living, breathing digital twin of reality?
It really makes you wonder where the technology is heading.
It's something to ponder as you step into the exam room. Good luck, everyone.